Our solar system has a secret. The textbooks end the story at Neptune. That's where the real adventure begins. You've been taught that empty space stretches beyond the giant planets. This assumption is spectacularly wrong. Tonight we're discovering the vast population of ancient ice worlds that patrol the outer darkness. We're examining why these frozen relics hold the keys to our cosmic origins. Before we dive into this frozen frontier, drop a comment about where you're listening from. If you enjoy these deep space journeys, consider subscribing. These explorations of the outer reaches are meant to be shared. Astronomers thought they had mapped everything. For over 2 centuries, Neptune marked the frontier. Beyond that empty void, this confidence would prove disastrously wrong. August 30, 1992 changed everything. 2 astronomers spotted something impossible. A faint speck crept across their telescope images. Too slow for an asteroid, too far for anything known. They called it 1992 QB1. That's just astronomer code for the first mysterious object we found in 1992. It orbited way beyond Neptune's territory. This wasn't just another rock floating in space. QB1 represented the first resident of an entirely hidden neighborhood, like finding the first house in a secret city. This discovery meant thousands more inhabitants were out there. Our solar system suddenly became much larger, more complex, more populated than anyone imagined. What seemed like empty space actually teemed with ancient worlds dancing in the darkness. Beyond Neptune lies an extraordinary preservation chamber. Think of the coldest freezer you can imagine. Then make it 1,000 times colder. That's where these ice worlds live. Temperatures drop to nearly 400 degrees below zero. Water becomes harder than granite. Methane gas freezes into solid rock. Nitrogen turns to ice. Everything that's liquid or gas on Earth becomes permanently frozen out there. This region stretches across billions of miles. Scientists call it the Kuiper Belt, a vast donut-shaped zone filled with cosmic leftovers. Hundreds of thousands of objects patrol this territory. Some are mountain-sized, others rival small planets. These worlds preserve the original recipe for planets, the materials that built Earth and the other planets. But closer to the Sun, heat destroyed most of these ancient ingredients. Only here, in the cosmic deep freeze, do they survive as perfect fossils from our solar system's birth. Pluto used to be special, the 9th planet, the lonely outpost at the solar system's edge. That story completely collapsed when astronomers found Pluto's neighbors. The neighbors started showing up in the late 1990s, object after object, some nearly as big as Pluto, some even bigger. Astronomers realized Pluto wasn't a unique planet at all. Pluto was just the largest resident in this icy neighborhood. Like discovering that what you thought was a mansion is actually just the biggest house on a crowded street. The street was full of similar houses you'd never noticed before. This discovery forced scientists to rewrite the definition of planet. Pluto got demoted to dwarf planet, a new category for these Kuiper Belt residents. The solar system suddenly had 8 planets instead of 9, but it gained hundreds of fascinating dwarf planets in return. For centuries, comets appeared like ghosts. They'd sweep in from nowhere, blaze across our skies, then disappear for decades or centuries. Nobody knew where they came from. Some comets return every few decades. Others take centuries to complete their journeys. Astronomers tracked their paths backward but couldn't find their origin. The trails led to empty space. The Kuiper Belt solved this ancient mystery. Those empty regions weren't empty at all. They were filled with billions of icy chunks. Some occasionally get bumped out of their orbits. They fall inward toward the sun. As they approach, the sun's heat transforms them. Their ice starts evaporating. They grow brilliant tails of gas and dust. They become the spectacular comets that light up our skies. Every comet you've ever seen was once a quiet resident of this frozen realm. The solar system you learned about in school was drastically incomplete. Textbooks showed 8 planets in a neat line. The story ended at Neptune. Reality is far more spectacular. The Kuiper Belt extends the solar system's boundary to twice its previously known size. Neptune sits about 3 billion miles from the Sun. The Kuiper Belt stretches to 7 billion miles out. Some objects venture even farther. This isn't just empty space with a few rocks scattered around. It's a densely populated cosmic suburb. The region contains more material than the asteroid belt between Mars and Jupiter, but it's spread across a vastly larger area. The solar system suddenly became a 2-story house instead of a ranch. The inner solar system, Mercury through Neptune, represents just the ground floor. The Kuiper Belt is the massive second story that astronomers had missed for centuries. These aren't cookie-cutter worlds. Each Kuiper Belt object tells its own story. Some glow reddish from ancient organic compounds. Others shine grey like dirty ice. Some spin so fast they've become football-shaped. Others rotate slowly like lazy tops. Many travel in pairs, 2 objects orbiting each other like a cosmic dance. Some have tiny moons of their own. A few even have thin atmospheres that change with the seasons. Yes, seasons. Even out there in the eternal cold. The largest objects show signs of geological activity. Ancient impact craters mark their surfaces. Some have smooth plains that suggest internal melting and refreezing. Others display complex patterns that hint at chemical reactions happening in the deep cold. Each world preserves a different chapter of solar system history. Some formed close to the Sun and got ejected outward. Others formed right where they sit now. Reading their surfaces is like reading pages from a 4.6 billion-year-old diary. These ice worlds don't just float randomly in space. They follow intricate patterns, like dancers in a cosmic ballet. Many objects orbit the Sun in nearly perfect step with Neptune. This happens because of something called orbital resonance. Think of it as cosmic music. Neptune completes 2 orbits while certain Kuiper Belt objects complete exactly 3. Or Neptune does 3 while they do 2. These mathematical relationships keep the dance stable for billions of years. The most famous example is Pluto itself. For every 2 times Pluto orbits the Sun, Neptune orbits exactly 3 times. This precise timing ensures they never collide despite their paths crossing on paper. They're locked in this gravitational waltz for eternity. This cosmic choreography reveals the hidden mathematical beauty underlying our solar system. What appears to be chaos from a distance is actually an intricate, stable pattern that's been playing out since the solar system formed. The ice worlds march to nature's most ancient rhythm. The Kuiper Belt preserves the solar system's birth certificate. These ice worlds contain materials that haven't changed since our cosmic neighborhood formed 4.6 billion years ago. They're like a library written in frozen chemicals. Scientists can read this library. They study the exact mix of water, methane, and other ices. Different ratios tell different stories. Some objects formed in the warm inner solar system before getting kicked outward. Others formed right where they orbit now. The chemical signatures reveal our solar system's violent youth. When giant planets migrated from their birth positions. When Jupiter and Saturn rearranged the entire cosmic architecture. When billions of objects got scattered like cosmic billiard balls. These frozen archives prove that our solar system was once drastically different. The planets didn't form where they sit today. They moved around, swapped positions, wreaked havoc on smaller objects. The ice worlds that survived this chaos still bear witness to our cosmic family's turbulent past. How cold can space actually get? The ice worlds beyond Neptune exist in temperatures that defy earthly experience. We're talking about cold so extreme that it changes the fundamental behavior of matter itself. At these distances from the Sun, temperatures drop to -375 degrees Fahrenheit. That's just 85 degrees above absolute zero, the theoretical coldest temperature possible in the universe. To put this in perspective, Antarctica's coldest recorded temperature is practically tropical compared to these ice worlds. This isn't just cold weather. It's a completely different physical environment. Materials that are gases on Earth become rock-hard solids. Water doesn't just freeze, it becomes harder than steel. Methane, nitrogen, and carbon monoxide all turn into permanent ice formations. The extreme cold acts like a cosmic preservation chamber. Chemical reactions that happen quickly on Earth slow to a virtual standstill. Radioactive decay continues, but heat dissipates so rapidly that internal temperatures barely rise above the frigid surface. This deep freeze environment explains why these worlds preserve materials unchanged since the solar system's formation. The cold doesn't just slow down chemical processes. It essentially stops time itself for these ancient ice worlds. What happens when the building blocks of life freeze solid for billions of years? The surfaces of these ice worlds contain familiar molecules arranged in completely unfamiliar ways. Nitrogen forms crystalline structures. Methane creates layered deposits. Water exists in multiple exotic ice phases. These aren't random mixtures. The different ices separate into distinct layers and regions based on their freezing points and chemical properties. The result is surface chemistry more complex than anything found on the rocky planets. Many objects show seasonal changes in their surface composition. As they orbit the Sun over hundreds of years, different ices sublimate and refreeze in endless cycles. The surfaces literally change chemistry with the seasons. Spectroscopic analysis reveals organic compounds throughout these ice worlds. These are carbon-based molecules, the same basic ingredients that led to life on Earth. But here they remain frozen in a pristine state, unchanged by billions of years of cosmic exposure. The surface chemistry of each world tells its unique story. Some objects preserve the original chemical composition of the solar nebula. Others show evidence of internal differentiation and surface processing. Each world represents a different outcome from the same basic set of chemical ingredients. These ice worlds break our assumptions about what solid objects should be like. Many have densities lower than water. They're not compact, solid masses. They're cosmic snowballs with more empty space than actual material. The low density comes from their porous internal structure. Instead of compacting under their own gravity like rocky planets, these worlds retain the fluffy texture of the original dust and ice that formed them. They're essentially frozen aggregations of the primordial solar system materials. Some objects have densities as low as 0.5 gram per cubic centimeter. That's half the density of water. If you could drop one of these worlds into a cosmic ocean, it would float like a cork. The porosity affects everything about these worlds. Sound would travel differently through their interiors. Impacts create different crater patterns. Heat flows through them in ways completely unlike solid rocky bodies. This fluffy structure preserves crucial information about planetary formation. These objects represent snapshots of the original accretion process, the gentle accumulation of dust and ice that built the first planetesimals billions of years ago. How fast should an ice world spin? There's no standard answer in the Kuiper Belt. These objects rotate at wildly different speeds, from frenzied 4-hour days to leisurely week-long rotations. The rotation periods appear almost random. Objects of similar size can have completely different spin rates. Some tiny worlds spin faster than much larger ones. The diversity suggests chaotic formation and collision histories. A few objects rotate so slowly that their days last longer than many comets' orbital periods. Others spin so rapidly they're stretched into distorted shapes by centrifugal force. The range spans more than 2 orders of magnitude. The rotation rates provide clues about these worlds' formation and collision histories. Fast rotators probably experienced energetic collisions that set them spinning. Slow rotators might represent gentler accretion or subsequent collision events that slowed them down. This rotational diversity demonstrates that the Kuiper Belt experienced a chaotic formation process. Unlike the organized rotation patterns of the major planets, these ice worlds preserve evidence of the violent, random collisions that characterized the early outer solar system. Can you have weather when it's 400 degrees below zero? Surprisingly, yes. Some larger Kuiper Belt objects maintain thin atmospheres that create genuine weather phenomena in the extreme cold. Pluto provides the best example of this alien meteorology. Its thin atmosphere consists mainly of nitrogen with traces of methane and carbon monoxide. Despite the extreme cold, this atmosphere circulates and creates weather patterns. The weather operates on completely different principles than Earth's systems. Instead of water evaporating, condensing, nitrogen and methane undergo phase changes. Frost forms and melts in seasonal cycles that last centuries. Atmospheric pressure on these worlds is incredibly low, thousands of times thinner than Earth's atmosphere. Yet even this gossamer thin gas creates noticeable surface changes over time. The existence of atmospheres this far from the Sun demonstrates that these worlds aren't completely dead. They maintain active surface processes driven by seasonal heating and cooling cycles. Even in the cosmic deep freeze, dynamic systems continue to reshape these distant worlds. What do landscapes look like after 4.5 billion years of cosmic impacts? The surfaces of these ice worlds preserve the most complete record of bombardment history in the solar system. Unlike rocky planets where erosion and geological activity erase impact craters, these frozen worlds preserve every major collision. Their surfaces are museums of cosmic violence stretching back to the solar system's formation. The crater patterns tell complex stories. Some regions show ancient, heavily cratered terrain dating to the earliest bombardment periods. Other areas display smooth plains that suggest more recent resurfacing events. Many objects show evidence of massive impact events that nearly shattered them entirely. Huge crater basins span significant fractions of their surfaces. Some impacts were so violent they created families of smaller objects from the debris. The preservation of this impact history provides invaluable data about the early solar system. These cratered surfaces record the intensity and timing of bombardment events that shaped all the planets. The ice worlds serve as cosmic history books written in craters and fractures. Large Kuiper Belt objects don't travel alone. Many have developed their own miniature solar systems complete with moons, rings, and complex gravitational relationships. The moon systems vary dramatically in complexity. Some objects have single large moons that probably formed from major impact events. Others host multiple small moons in intricate orbital patterns. The most spectacular example is Haumea's ring system. This elongated world is surrounded by a thin ring of debris, probably created by a collision with one of its moons. The ring particles orbit in perfect synchronization with Haumea's rapid rotation. Binary systems are surprisingly common. Many objects exist as contact binaries, two separate worlds barely touching each other. Others orbit as widely separated pairs held together by weak gravitational bonds. These complex systems demonstrate that gravitational dynamics operate at all scales in the Kuiper Belt. Even relatively small objects can capture moons and maintain stable orbital relationships for billions of years. The ice worlds have become gravitational architects, constructing their own miniature versions of planetary systems. Why do some ice worlds change color over time? Observations spanning decades reveal that the surfaces of these objects undergo gradual but measurable color shifts that reflect ongoing chemical processes. The color changes result from space weathering, the gradual alteration of surface materials by cosmic radiation and solar wind particles. High-energy radiation breaks apart surface molecules and creates new compounds with different optical properties. Most objects gradually become redder and darker over time. The radiation processing creates complex organic compounds that absorb blue light more efficiently than red light. The result is a slow transformation from bright, neutral colors to dark, reddish hues. Some objects show more dramatic color variations across their surfaces. Different regions appear to age at different rates, possibly due to variations in composition or exposure to radiation. These ongoing color changes provide a real-time window into surface evolution processes. Unlike most astronomical phenomena that occur over geological timescales, surface weathering operates fast enough for human observers to detect. The ice worlds are slowly transforming their appearances during our lifetimes. What's inside an ice world? Despite their fluffy overall density, many large objects have undergone internal differentiation. The separation of different materials into distinct layers based on density and composition. The differentiation process requires internal heat sources. Radioactive decay of long-lived isotopes provides the energy needed to partially melt and reorganize the interior structure. Larger objects retain heat more efficiently and show more complete differentiation. The resulting internal architecture resembles a cosmic layer cake. Dense rocky materials sink toward the center. Water ice forms intermediate layers. Lighter ices like methane and nitrogen concentrate near the surface. This layered structure affects surface geology and evolution. Objects with differentiated interiors can maintain subsurface oceans for billions of years. They're more likely to experience geological activity and surface renewal. The degree of internal organization varies dramatically between objects. Small ice worlds remain relatively undifferentiated. Larger ones show evidence of complex internal structure that rivals the major moons of the giant planets. The collision history of the Kuiper Belt reads like a cosmic war zone. Every ice world bears the scars of billions of years of impacts, collisions, and near-miss encounters that shape their current forms. The collision environment has evolved over time. Early in solar system history, the Kuiper Belt was much more densely populated. Collisions were frequent and energetic. Most small objects got destroyed or merged into larger ones. Different types of collisions produce different outcomes. High-speed impacts completely destroy both objects, creating debris clouds that may eventually reassemble into loose rubble piles. Lower-speed collisions can strip away surface layers or create large crater systems. Some objects show evidence of catastrophic disruption followed by reassembly. They exist as rubble pile structures held together primarily by gravity. These loose aggregations represent the reassembled fragments of ancient collision events. The collision history explains the diverse shapes, compositions, and orbital properties of modern Kuiper Belt objects. Each world represents a unique outcome from billions of years of cosmic violence. The survivors we observe today are the fortunate remnants of a much larger population that didn't survive the bombardment lottery. Pluto defied every prediction. Scientists expected a dead, frozen ball of ice, a cosmic fossil with nothing happening on its surface. They couldn't have been more wrong. NASA's New Horizons spacecraft arrived at Pluto in 2015. The images it sent back stunned the scientific world. Pluto wasn't dead at all. It was vibrantly alive with geological activity. The surface revealed vast nitrogen plains, smooth as a skating rink, fresh and unmarked by asteroid impacts. This meant the plains were geologically young, maybe just a few million years old. On cosmic timescales, that's practically yesterday. Mountain ranges stretched across the landscape, made of water ice hard as rock at those temperatures. Some peaks rose over 2 miles high. Methane dunes, actual sand dunes made of frozen methane, marched across the plains like earthly deserts. This distant world had weather, seasons, atmospheric circulation, complex chemistry happening on its surface. Pluto proved that even in the outer darkness, worlds can remain dynamic and fascinating. Size doesn't determine activity. Internal heat and chemical processes do. What makes a planet a planet? For decades, nobody questioned this. Then astronomers discovered Eris. This discovery shattered our comfortable assumptions about planetary status. Eris appeared in telescope images in 2005. At first glance, it seemed like another Kuiper Belt object, but careful measurements revealed something shocking. Eris was more massive than Pluto. This created an impossible situation. If Pluto qualified as our solar system's 9th planet, then Eris clearly deserved planetary status too. But that would mean admitting we'd missed a 10th planet for years. It would also mean dozens more planets were likely waiting to be discovered in the outer solar system. Astronomers faced a choice: either dramatically expand the number of planets, or create a new category. They chose the latter. In 2006, they invented the term dwarf planet. Both Pluto and Eris became charter members of this new class. The solar system officially dropped from 9 planets to 8. But it gained a whole new category of fascinating worlds that didn't quite fit the traditional planetary mold. Makemake presents astronomers with a chemical mystery. This world shines brighter than it should. Its surface reflects light like fresh snow. But the composition tells a much more complex story. Spectroscopic analysis, basically reading the colors of light bouncing off Makemake, reveals a surface covered in multiple types of ice. Methane ice dominates large regions. Ethane ice fills in other areas. These aren't just randomly mixed together. The methane appears to be constantly refreshing itself. This could suggest active geological processes. Either methane geysers erupting from the interior, or seasonal changes that redistribute surface materials. Both scenarios would require internal energy sources. The brightness itself poses questions. Most objects in the Kuiper Belt are darker than charcoal. Constant bombardment by cosmic radiation should darken their surfaces over millions of years. Makemake's brilliant reflectivity suggests its surface gets regularly renewed. This world maintains a complex chemical landscape despite its distance from the Sun. Something keeps reshaping and refreshing its surface. Whether it's internal geology or atmospheric processes, Makemake refuses to behave like a simple frozen rock. Haumea broke the rules of planetary formation. Most large objects in space end up roughly spherical. Gravity pulls everything toward the center. Over millions of years, this creates ball-shaped worlds. Haumea decided to be different. This dwarf planet spins faster than any other known object of its size. One day on Haumea lasts just 4 hours. That's 6 times faster than Earth's rotation. This breakneck has transformed its entire shape. Instead of a sphere, Haumea resembles a cosmic football, stretched and flattened by its own rotation. The centrifugal force, the same force that pushes you outward on a spinning carnival ride, overpowers gravity at the equator. Scientists estimate Haumea stretches about 1,500 miles at its widest point, but only 600 miles from pole to pole. That makes it one of the most distorted large objects in our solar system. This extreme shape reveals Haumea's violent history. Something massive must have collided with it billions of years ago. The impact shattered pieces off and set the remaining core spinning like a cosmic top. The collision was so powerful it created Haumea's own family of small moons from the debris. Sedna follows a path that defies explanation. While most Kuiper Belt objects orbit relatively close to the Sun, Sedna ventures into the cosmic wilderness. Its orbit stretches farther than almost any other known object in our solar system. At its closest approach, Sedna still sits 3 times farther from the Sun than Neptune. At its farthest point, it travels 900 times Earth's distance from the Sun. One complete orbit takes approximately 11,000 years. This extreme path places Sedna in uncharted territory. Too far to be influenced by the known planets. Too close to have come from interstellar space. Astronomers call this region the inner Oort cloud, transitional zone between our solar system and the space between stars. Sedna's orbit suggests our solar system's history was more chaotic than we thought. Either a massive planet once existed in the outer reaches and got ejected, or our Sun had a close encounter with another star billions of years ago. Both scenarios would explain how Sedna ended up on such an impossible trajectory. This lonely world connects our solar system to the vast Oort cloud that surrounds it. Sedna proves that the boundary between our cosmic neighborhood and interstellar space isn't clean and simple. It's a gradual transition filled with rebel worlds, following their own mysterious rules. Orcus earned the nickname Anti-Pluto for good reason. This dwarf planet shadows Pluto's orbital path. When Pluto reaches its closest point to the Sun, Orcus sits at its farthest. When Pluto swings out to its maximum distance, Orcus approaches its nearest point. This isn't coincidence. Orcus and Pluto are locked in what astronomers call a gravitational resonance. They're like dance partners who never touch, but move in perfect synchronization. This cosmic choreography has continued for billions of years. Both worlds share remarkably similar characteristics, nearly identical orbital periods, comparable sizes. Both have large moons relative to their own size. Even their surface compositions show striking similarities. Dark reddish terrain mixed with brighter patches. The resemblance extends to their moons. Pluto's moon Charon spans about half Pluto's diameter. Orcus has a moon called Vanth that's proportionally just as large. These moon systems probably formed the same way, through massive collisions early in solar system history. This cosmic symmetry reveals how gravitational forces sculpt the outer solar system. Orcus and Pluto represent twin outcomes from similar formation processes. They prove that the Kuiper Belt produces families of related objects, not just random collections of ice and rock. Varuna challenges our assumptions about what counts as a single world. This object appears to be two separate dwarf planets that merged into one. Astronomers call this configuration a contact binary, two objects touching but still somewhat distinct. Computer models suggest Varuna formed when two large Kuiper Belt objects collided at very low speed. Instead of shattering into fragments, they stuck together, like two snowballs gently pressed into one larger snowball. The merger wasn't perfect. Varuna retains a distinctly bilobed shape, like a cosmic peanut. Each lobe probably represents one of the original objects. The collision created a narrow neck where they joined together. This formation process might be common in the Kuiper Belt. Low-speed collisions happen frequently in the outer solar system. Objects move slowly due to the weak gravitational forces. When they do collide, they're more likely to merge than shatter. Varuna demonstrates how dwarf planets grow through accretion, not just from collecting dust and small rocks, but by absorbing other large objects. This contact binary represents planetary formation in action, a process that's still happening in the outer reaches of our solar system. Quasar accomplished something that should have been impossible. This dwarf planet managed to pull itself into a nearly perfect sphere despite being much smaller than expected for such a shape. Gravity creates spherical worlds, but only if the object is massive enough. Smaller objects lack sufficient gravitational force to overcome their own structural strength. They remain lumpy and irregular, like most asteroids and small moons. Scientists calculated that objects need to be at least 600 miles across to become spherical. Quasar measures just 700 miles in diameter. That puts it barely over the threshold, yet its shape is remarkably round. This perfect sphericity suggests Quasar once contained significant internal heat. Early radioactive decay probably warmed its interior. The heat made the rocky and icy materials soft enough for gravity to reshape the entire body into a sphere. The achievement becomes more impressive considering Quasar's composition. It's roughly half rock and half ice. That mixture should make it harder to deform than pure ice objects. Yet Quasar succeeded in becoming round while many larger objects remain irregular. Ixion stands out for its dramatic coloration. This dwarf planet glows deep red like a cosmic ruby. The color isn't just surface decoration. It tells a story about the solar system's earliest chemistry. The red hue comes from organic compounds, complex carbon-based molecules that formed billions of years ago. These are some of the same materials that existed in the original solar nebula, the cloud of gas and dust that gave birth to our entire solar system. Cosmic radiation gradually transforms these organic compounds. Over millions of years, the radiation breaks apart simple molecules and creates more complex ones. This process, called radiation processing, creates the distinctive reddish coloration. Ixion's intense red color suggests its surface has remained unchanged for billions of years. No recent impacts have excavated fresh material from below. No geological activity has resurfaced the terrain. The deep red represents an ancient patina of cosmic chemistry. This preservation makes Ixion a time capsule. Its surface chemistry provides clues about conditions in the early solar system. The organic compounds it contains might be similar to the materials that eventually led to life on Earth. Ixion preserves a chemical record of our cosmic origins written in brilliant red. Pholus follows one of the most inclined orbits in the Kuiper Belt. While most objects circle the Sun roughly in the same plane as the planets, Pholus travels at a steep angle. Its orbital path tilts more than 24 degrees from the planetary plane. This extreme inclination tells a story of gravitational warfare. Something powerful knocked Pholus out of its original orbital plane. The most likely culprit is Neptune itself. During the early solar system's chaotic period, Neptune migrated outward from its birth position. As Neptune moved, its gravity scattered countless Kuiper Belt objects. Some got ejected entirely. Others had their orbits stretched into elongated shapes. A few, like Pholus, got tilted out of the main plane of the solar system. Despite this gravitational beating, Pholus maintains a special relationship with Neptune. The two bodies are locked in a 3-to-2 orbital resonance. For every 3 times Neptune orbits the Sun, Pholus completes exactly 2 orbits. This resonance acts like a gravitational lifeline. It prevents Pholus from colliding with Neptune despite their complex orbital dance. The same gravitational force that tilted Pholus's orbit now protects it from destruction. This cosmic relationship has remained stable for billions of years. Why don't these ice worlds crash into each other? With thousands of objects orbiting in the same region, collisions should be constant. Yet most Kuiper Belt objects maintain stable, predictable paths for billions of years. The answer lies in something called orbital resonance. This is nature's way of keeping cosmic traffic organized. Think of it like a perfectly timed traffic light system that prevents accidents at busy intersections. Here's how it works. Some Kuiper Belt objects complete exactly 2 orbits while Neptune completes 3. Others finish 3 orbits while Neptune does 5. These mathematical relationships aren't coincidence. They're gravitational locks. Neptune's massive gravity acts like a cosmic conductor. It orchestrates the movements of distant objects through invisible gravitational threads. When objects try to drift into chaotic orbits, Neptune's influence gently guides them back into stable patterns. This resonance system has kept the outer solar system organized since its formation. Without these gravitational relationships, the Kuiper Belt would have dissolved into chaos billions of years ago. Instead, mathematical harmony rules the outer darkness. What makes Pluto special isn't its size or composition. It's the exclusive gravitational club it belongs to. Pluto is the most famous member of a group astronomers call Plutinos, worlds that share Pluto's special orbital relationship with Neptune. All Plutinos follow the same gravitational rule. They complete exactly 2 orbits around the Sun for every 3 Neptune orbits. This 2-to-3 ratio creates a stable gravitational zone in the outer solar system. The club has hundreds of members. Each one is locked into this same mathematical relationship with Neptune. Despite their widely different sizes and compositions, they all march to the same gravitational beat. This membership comes with exclusive benefits. Plutonos can cross Neptune's orbital path without ever colliding with the giant planet. Their special timing ensures they're always in the wrong place for a collision. The gravitational handshake between Plutonos and Neptune has lasted for billions of years. It's one of the most stable relationships in the solar system. This cosmic partnership protects Pluto and its fellow club members from gravitational chaos. Not all Kuiper Belt objects follow Pluto's leisurely pace. Some ice worlds chose the fast lane. They orbit much closer to Neptune and complete their journeys in less time. These speedsters belong to a group called the classical Kuiper Belt. They occupy the region just beyond Neptune's orbit. Their proximity to the Sun makes them cosmic race cars compared to their distant cousins. Many resonant objects in this broader region maintain a different relationship with Neptune. They follow a 3-to-2 resonance instead of Pluto's 2-to-3 pattern. This means they complete 3 orbits while Neptune finishes 2. The faster pace comes with trade-offs. These objects face stronger gravitational influences from Neptune. They experience more orbital perturbations, small changes that gradually shift their paths over millions of years. Despite the challenges, the classical Kuiper Belt represents one of the most densely populated regions of ice worlds. The faster orbits and stable resonances create ideal conditions for preserving large populations of ancient objects in a relatively compact cosmic neighborhood. Some ice worlds tell stories of cosmic violence. These scattered objects follow highly stretched orbits that carry them far from their birthplaces. Their extreme paths reveal the chaotic history of the outer solar system. Unlike the organized residence of stable resonances, scattered objects follow unpredictable routes. Some venture nearly twice as far as Pluto before returning. Others swing closer to the Sun than Neptune itself. These elongated orbits are battle scars from gravitational encounters with Neptune. Billions of years ago, as Neptune migrated outward, it scattered countless objects like cosmic billiard balls. Most got ejected entirely. The survivors became the scattered disk population. Each scattered object carries the memory of its violent encounter. The more extreme the orbit, the more dramatic the original scattering. Some objects got barely nudged into slightly elliptical paths. Others got hurled into interplanetary exile. The scattered disk proves that the outer solar system wasn't always the peaceful, organized place we see today. It was once a war zone where migrating giant planets wreaked havoc on smaller worlds. The scattered objects are the refugees from that ancient cosmic conflict. Beyond the scattered disk lies a realm of true independence. Here, ice worlds follow their own rules. Too distant for Neptune to control, these objects represent the solar system's most isolated residents. Astronomers call them detached objects. The name perfectly describes their situation. They've broken free from direct planetary gravitational control. They orbit in splendid isolation at the solar system's edge. These worlds follow long, stable paths. Without strong planetary interference, their orbits can remain predictable for vast stretches of time. But they're so distant that completing one orbit takes thousands of years. The detached population bridges our solar system and interstellar space. They occupy the boundary zone where the Sun's gravity begins to weaken. Beyond them lies the Oort cloud, a spherical shell of comets surrounding our entire solar system. These cosmic hermits may hold clues about the solar system's formation. Their isolation preserved them from the gravitational chaos that reshaped the inner Kuiper Belt. They represent some of the most pristine samples of the original planetesimal disk that surrounded our young Sun. Some ice worlds perform the most complex dance in the solar system. They follow interconnected orbits that weave between multiple partners. Astronomers call these elaborate patterns quasi resonances, gravitational waltzes that can last for millions of years. In a quasi resonance, an object's orbit tilts up and down like a cosmic seesaw. As the tilt increases, the orbit can become more circular. As the tilt decreases, the orbit can stretch into an elongated shape. This oscillation happens on vast timescales. One complete cycle might take several million years. During this time, the ice world's orbital distance and shape undergo dramatic transformations. The dance partners aren't always obvious. Sometimes Jupiter and Neptune work together to control a distant object's motion. Other times, the influence comes from the entire population of giant planets acting collectively. These complex relationships demonstrate that the outer solar system operates as an interconnected system. Every object influences every other object through gravitational threads. The result is a cosmic choreography of stunning mathematical beauty and complexity. Ice world orbits aren't frozen in time. They evolve slowly like cosmic glaciers carved by gravitational forces. This process happens so gradually that astronomers call it secular evolution. Changes that accumulate over geological timescales. The evolution follows predictable patterns. Orbital shapes oscillate between circular and elongated. Orbital planes tilt up and down relative to the planetary disk. These changes cycle back and forth over millions of years. The driving force comes from subtle gravitational influences. Distant planets exert weak but persistent tugs on ice world orbits. Over millions of years, these gentle influences accumulate into dramatic changes. Some ice worlds experience cycles that last 20 million years. During each cycle, their orbits transform from nearly circular to highly elongated and back again. The objects themselves remain stable, but their paths through space constantly evolve. This slow evolution explains why the Kuiper Belt contains such diverse orbital families. Objects that started with similar orbits have gradually separated into distinct groups. The secular evolution acts like a cosmic sorting mechanism, organizing ice worlds into their current categories. Not every region of the outer solar system provides stable housing. Hidden between the organized neighborhoods lie gravitational danger zones. Objects that wander into these regions face orbital destruction. These chaotic zones exist wherever different resonances overlap. Imagine standing at the intersection of multiple ocean currents. The conflicting flows create turbulence and unpredictability. Gravitational resonances work the same way. An ice world entering a chaotic zone experiences rapidly changing gravitational forces. Its orbit becomes unpredictable. Computer simulations show that most objects in chaotic zones get ejected from the solar system within a few million years. The boundaries between stable and chaotic regions are surprisingly sharp. An object can orbit peacefully for billions of years. Then a small gravitational nudge pushes it across an invisible line into chaos. Within a few orbits, its path becomes completely unpredictable. These gravitational badlands explain why certain regions of the Kuiper Belt appear empty. Objects that once orbited there have been cleared out by chaotic dynamics. The empty zones serve as gravitational graveyards, reminders of the cosmic violence that shapes the outer solar system. Ice world orbits don't just evolve, they migrate. Over millions of years, gravitational forces slowly shepherd objects from one orbital family into another. This cosmic urban planning reshapes the entire outer solar system. The migration happens through a process called diffusion. Random gravitational encounters gradually change an object's orbit. Like a drunk person's walk, each step seems random, but the overall path follows predictable statistical patterns. Most migration flows outward. Objects slowly drift away from the Sun into more distant orbits. This happens because encounters with Neptune tend to add energy to orbits rather than remove it. The process takes extraordinary patience. A typical migration from one orbital family to another requires several million years. That's longer than complex life has existed on Earth. Yet in cosmic terms, it's relatively rapid evolution. This orbital migration explains how the Kuiper Belt maintains its current structure. Despite billions of years of gravitational stirring, the system remains organized. Migration acts like a cosmic conveyor belt, continuously moving objects between different orbital neighborhoods while maintaining overall stability. Jupiter's influence extends far beyond its obvious gravitational neighborhood. This giant planet reaches across the entire solar system to subtly perturb ice-world orbits. Even at distances about 50 times farther than Jupiter's own orbit, its gravitational fingerprints remain detectable. The perturbations work through a cosmic game of telephone. Jupiter doesn't directly influence most Kuiper Belt objects. Instead, it affects Saturn, which affects Neptune, which finally affects the ice worlds. This gravitational cascade emits transitors' influence across billions of miles. The effects are subtle but measurable. Jupiter's gravity causes tiny changes in Neptune's orbit. These changes alter the timing of Neptune's gravitational tugs on distant objects. Over millions of years, these microscopic effects accumulate into detectable orbital changes. Computer simulations reveal Jupiter's hidden role in sculpting the outer solar system. Without Jupiter's gravitational participation, the Kuiper Belt would be organized differently. Many orbital resonances that exist today would be missing or shifted to different locations. This long-distance relationship demonstrates that the solar system operates as a single, integrated gravitational machine. Every planet influences every other object through invisible threads of gravitational force. Jupiter serves as a master controller in this system, shaping cosmic dynamics across distances that dwarf human comprehension. Picture the early solar system as a giant rotating pancake of gas and dust. The sun blazed at the center, but far from its heat, something magical was happening in the outer regions. Here, temperatures dropped low enough for water to freeze. Not just water. Methane, ammonia, and carbon dioxide all turned solid. These weren't tiny snowflakes. They were microscopic ice grains floating in the cosmic void. This was where the ice worlds began their journey, in what astronomers call the protoplanetary disk, the original cloud of material surrounding our newborn sun. The freezing process created the raw materials for everything we see in the Kuiper Belt today. Without this early ice formation, there would be no frozen worlds beyond Neptune, no Pluto, no comets, no icy moons. This cosmic snow line, the boundary where ice could form, determined the entire architecture of our solar system. Inside this line, only rocky planets could grow. Outside it, ice giants and frozen worlds dominated. The Kuiper Belt exists because our solar system had the perfect temperature gradient to create this icy assembly line. How do you build a world from cosmic dust? Start small and be patient, very patient. The process took millions of years and countless gentle collisions. It began with ice grains smaller than rice. These tiny particles drifted through space, occasionally bumping into each other. When they collided gently, they stuck together instead of bouncing apart. Gradually, these clusters grew larger, from rice-sized grains to pebbles, from pebbles to boulders, from boulders to mountains. Each collision added more material to the growing chunks. Scientists call these growing objects planetesimals, basically baby planets still under construction. The Kuiper Belt region was filled with millions of these construction projects happening simultaneously. The process required a delicate balance. Collisions needed to be gentle enough for materials to stick together, but energetic enough to overcome the weak gravitational forces. Too violent, and the growing objects would shatter. Too gentle, and they'd just bounce off each other like cosmic billiard balls. The early Kuiper Belt didn't look anything like today's version. It was much denser, more populated, and closer to the sun. Then the giant planets started moving, and everything changed forever. Neptune wasn't always where it sits today. It formed much closer to the sun. But gravitational interactions with Jupiter caused Neptune to migrate outward like a cosmic bulldozer. As Neptune moved, it encountered the original Kuiper Belt population. The gravitational chaos was absolute. Neptune's massive gravity scattered ice worlds in every direction. Some got hurled toward the inner solar system. Others got ejected completely. The migration was neither quick nor gentle. It took hundreds of millions of years. During this entire period, the Kuiper Belt experienced constant gravitational bombardment. This planetary migration explains why today's Kuiper Belt seems so empty compared to computer models of the original population. Neptune's outward journey destroyed the primordial ice world neighborhood and replaced it with the sparse, organized structure we observe today. Neptune's migration didn't affect all ice worlds equally. The giant planet's gravity created a cosmic sorting machine. Some objects got special treatment. Others faced immediate eviction. The lucky ones found themselves captured in orbital resonances. These gravitational safe harbors protected them from Neptune's destructive influence. Objects that landed in the 2 to 3 resonance became the Plutinos. Those in other resonances formed different stable families. The unlucky majority faced a different fate. They got scattered across the outer solar system. Some landed in highly elliptical orbits. Others got ejected entirely from the solar system. The sorting process wasn't random. It depended on precise timing and positioning. Objects in exactly the right places at the right times found stable homes. Everything else got swept away by the gravitational storm. This great sorting explains why the modern Kuiper Belt contains distinct populations with different characteristics. Each group represents survivors from a different part of the original chaos. The resonant objects are the refugees who found shelter. The scattered objects are the homeless wanderers, still feeling the effects of their ancient displacement. Something dramatic happened about 600 million years after the solar system formed. The entire planetary system suddenly became unstable. Astronomers often call this event the Late Heavy Bombardment, a period when chaos may have ruled the solar system. The instability started with the giant planets. Their orbits had been slowly changing since formation. Eventually, they reached a configuration that couldn't last. Like a house of cards reaching its limit, the whole system collapsed into chaos. Jupiter and Saturn crossed into a 2-to-1 orbital resonance. This created powerful gravitational interactions that destabilized everything. Uranus and Neptune got scattered to new orbits. The ice giant planets may even have swapped positions multiple times. The chaos lasted for several hundred million years. During this period, planetary orbits constantly shifted. Some moons got captured, others got ejected, asteroid populations got scrambled, comet reservoirs got depleted. This instability period may explain many puzzling features of our solar system. Why the outer planets have such different characteristics. Why certain asteroid populations exist where they do. Why the Kuiper Belt has its current structure. The late heavy bombardment may have been the solar system's most transformative period since its initial formation. For decades, astronomers couldn't explain the modern Kuiper Belt structure. Computer simulations of planetary formation never produced anything resembling what we observe today. Then a team in Nice, France, cracked the code. The Nice model, named after the city where it was developed, proposed that planetary migration could explain everything. The model suggested that Jupiter moved inward, while the ice giants moved outward during the solar system's youth. When astronomers ran this scenario through their computers, something remarkable happened. The simulations produced Kuiper Belt populations that closely matched observations. The right number of Plutinos, the correct scattered disk structure, even the proper orbital inclinations. The model revealed that apparent chaos could create stable order. The violent planetary migrations, which seemed destructive, actually organized the outer solar system into its current configuration. This computational breakthrough transformed our understanding of solar system formation. It showed that the planets didn't form in their current positions. Instead, they migrated vast distances while sculpting the architecture we see today. The NICE model suggested that our solar system's history was far more dynamic and violent than anyone had imagined. The early Kuiper Belt was a bustling cosmic city, densely packed with objects, frequent interactions, constant activity. Today's sparse population represents the survivors of a once thriving community. Computer models suggest the original Kuiper Belt contained 200 times more material than exists today. That's equivalent to several Earth masses worth of ice and rock. The early belt stretched much closer to the Sun and contained objects of every size. Most of this primordial population got eliminated during planetary migration. Some objects collided with migrating planets. Others got ejected into interstellar space. Still others crashed into the inner solar system during the late heavy bombardment. The survivors represent less than 1% of the original population. They're like the few residents who remained in a city after a massive disaster. Their current locations and orbits bear little resemblance to their original neighborhood. This massive depopulation explains why the modern Kuiper Belt seems relatively empty. What we observe today isn't the original structure. It's the remnant after billions of years of gravitational evacuation. The real Kuiper Belt formation story is one of destruction and survival, not steady construction. Imagine if Earth suddenly lost 99% of its mass. That's essentially what happened to the Kuiper Belt during the solar system's chaotic youth. The mass was so extreme it fundamentally changed the region's character. The original Kuiper Belt contained enough material to build multiple Earth-sized planets. Gravitational interactions were frequent and energetic. The region buzzed with constant activity. Planetary migration stripped away most of this material. Objects got scattered in every direction. Some crashed into the giant planets. Others got ejected beyond the solar system's edge. Only a tiny fraction remained in stable orbits. The mass loss created a feedback effect. With fewer objects remaining, gravitational interactions became rarer. The surviving population settled into more stable configurations. The violent early period gave way to the relatively quiet modern era. This dramatic mass reduction explains many puzzling aspects of the current Kuiper Belt. Why collisions are so rare despite thousands of objects sharing the same region. Why the orbital families are so well organized. Why the belt appears underdense compared to theoretical predictions. The answer is simple. Most of the original material is gone. Collisions weren't just common in the early Kuiper Belt. They were unavoidable. With 200 times more objects packed into the same space, impact events happened constantly. These cosmic crashes shaped every world we see today. The collision rate was absolutely staggering. Large impacts occurred every few thousand years instead of every few million years. Objects couldn't grow larger than a few hundred miles before getting shattered by the next major collision. Each impact told a different story. High-speed collisions completely destroyed both objects, creating clouds of debris. Lower-speed impacts broke objects apart, but allowed the pieces to reassemble into loose rubble piles. The collision environment gradually calmed as planetary migration removed most objects. Fewer targets meant fewer impacts. The surviving objects could finally grow larger without getting immediately destroyed. This collision history explains the diverse surface features we observe on modern Kuiper Belt objects. Ancient impact craters mark the locations of early collisions. Smooth plains suggest later impacts that melted and resurfaced entire regions. The varied compositions result from mixing materials during countless cosmic crashes. The ice worlds of the Kuiper Belt didn't just change physically during their evolution. Their chemical composition underwent dramatic transformations too. Simple water ice evolved into complex organic chemistry that rivals anything found on Earth. The transformation started with radioactive decay. Early ice worlds contained radioactive elements left over from the solar system's formation. As these elements decayed, They released heat that drove chemical reactions inside the objects. Cosmic radiation also played a crucial role. High-energy particles from space constantly bombarded ice world surfaces. This radiation broke apart simple molecules and created more complex compounds. Over billions of years, the surfaces became rich in organic materials. Some objects experienced more dramatic chemical changes. Large impacts melted their interiors, allowing different materials to separate and react. The heat created conditions similar to those in Earth's early oceans, perfect for complex chemistry. This chemical evolution explains why Kuiper Belt objects display such varied colors and compositions today. Each world represents a different outcome from billions of years of chemical processing. The gray and brown surfaces we observe are chemical fingerprints of this complex evolutionary history. Orbital resonance sounds complicated, but it's actually nature's simplest organizing principle. Think of two pendulum clocks hanging on the same wall. Eventually they start swinging in perfect sync. That's resonance, the tendency of systems to lock into mathematical relationships. In the Kuiper Belt, this happens between orbital periods. Some ice worlds complete exactly 2 orbits while Neptune finishes 3. Others do 3 orbits while Neptune does 5. These aren't coincidences, they're gravitational locks. The mathematical ratios create stability that lasts billions of years. When an object tries to drift out of its resonant timing, Neptune's gravity gently pulls it back into sync. It's like a cosmic metronome keeping perfect time. These simple integer ratios, 2 to 3, 3 to 5, 4 to 7, govern the motion of thousands of ice worlds. Each ratio represents a different gravitational parking space in the outer solar system. The resonant relationships provide long-term orbital insurance. Objects in resonance can maintain stable orbits for the entire lifetime of the solar system. Without these mathematical partnerships, most Kuiper Belt objects would have been scattered into chaos long ago. Neptune didn't start where it sits today. As the ice giant migrated outward during the solar system's youth, it carried passengers along for the ride. This cosmic kidnapping created most of the resonant populations we observe today. Picture Neptune as a slow-moving gravitational bulldozer. As it pushed outward, its gravity caught objects in what astronomers call resonance capture. Ice worlds got swept up and carried along in specific orbital relationships. The capture process was incredibly selective. Only objects at precisely the right distances and speeds got trapped. Everything else either got scattered away or remained behind in non-resonant orbits. Most Plutinos, objects sharing Pluto's 2 to 3 resonance with Neptune, formed through this capture mechanism. They weren't born in their current orbits. They got kidnapped during Neptune's migration and forced into their present configuration. This migration dragnet explains why resonant objects cluster in specific orbital families. Each family represents survivors from a different phase of Neptune's outward journey. The resonant populations are living fossils from the era of planetary migration. Not every ice world stays trapped in resonance forever. Some manage to escape their gravitational chains and venture into the chaotic regions beyond. These cosmic escape artists reveal the limits of Neptune's organizational control. Resonance escape happens when an object receives a strong gravitational kick. This might come from a close encounter with another ice world, or from the cumulative effects of multiple small perturbations over millions of years. Once an object breaks free from resonance, its orbital evolution becomes unpredictable. Without the stabilizing influence of the resonant relationship, it faces gravitational chaos. Most escaped objects eventually get ejected from the Kuiper Belt entirely. The escape process isn't instantaneous. Objects can drift in and out of resonance multiple times before making their final break. Some spend millions of years in unstable transition zones before committing to escape. These liberated objects provide crucial clues about the dynamical evolution of the outer solar system. Their current orbits preserve the history of their escape events. Each escaped object tells a story of gravitational drama played out over cosmic timescales. The 2 to 3 resonance with Neptune hosts the largest and most stable population of ice worlds. This gravitational sweet spot provides the perfect balance of stability and orbital freedom for thousands of objects. Pluto is the most famous resident of this orbital neighborhood, but it shares the space with hundreds of other objects called Plutinos. They all follow the same basic rule: 2 orbits around the Sun for every 3 Neptune orbits. This 2 to 3 timing creates remarkable orbital stability. Objects can maintain their resonant relationship for billions of years without disruption. The mathematical relationship acts like gravitational glue holding the population together. The resonance width is surprisingly generous. Objects don't need to maintain perfect 2 to 3 timing to remain stable. Small deviations from the exact ratio are allowed and automatically corrected by Neptune's gravitational influence. This flexibility explains why the 2 to 3 resonance became so densely populated during planetary migration. Its wide capture zone and strong stability made it the most successful refuge for ice worlds fleeing the chaos of Neptune's outward journey. Higher-order resonances operate like gravitational whispers rather than shouts. These weak but persistent influences create subtle orbital patterns that unfold over millions of years. Unlike the obvious 2 to 3 and 3 to 4 resonances, higher-order relationships involve more complex ratios. Objects might complete 7 orbits while Neptune does 12, or 11 orbits while Neptune finishes 19. These intricate relationships are harder to detect but equally important for long-term stability. The effects accumulate slowly over vast timescales. Small orbital adjustments build up gradually until they produce measurable changes in an object's path. What appears random on short timescales reveals hidden order over millions of years. Computer simulations show these weak resonances filling gaps between the stronger ones. They create a complex network of gravitational influence that extends throughout the Kuiper Belt. This resonant web demonstrates that no ice world orbits in complete isolation. Even the weakest mathematical relationships can exert meaningful control over orbital evolution. The outer solar system operates as an interconnected gravitational ecosystem, where every object influences every other object through invisible threads of mathematical harmony. Some ice worlds experience a peculiar form of orbital instability that actually increases their long-term survival chances. This counterintuitive phenomenon involves orbits that oscillate between different shapes and tilts over millions of years. The Kozai mechanism, named after the astronomer who first described it, creates these long-term orbital seesaws. An object's orbit alternately becomes more circular and more elliptical in a regular cycle. Simultaneously, the orbital tilt oscillates up and down. Each complete cycle takes several million years to finish. During this time, the ice world's distance from the Sun changes dramatically, but the oscillations are perfectly predictable and stable. The mechanism works through the combined gravitational influence of multiple giant planets. Jupiter, Saturn, and Neptune work together to create these complex orbital patterns. The result is a slow-motion gravitational dance that continues for billions of years. Objects caught in Kozai oscillations gain protection from chaotic orbital evolution. The regular oscillations prevent them from wandering into unstable regions of orbital space. This cosmic seesaw effect actually enhances long-term orbital survival in the outer solar system. Resonances aren't razor-thin mathematical lines in space. They're broad zones of gravitational influence with comfortable margins for error. Ice worlds can drift significantly from perfect resonant timing without losing their orbital protection. Think of resonance width like a cosmic highway lane. Objects don't need to follow the exact center line to stay safe. They can weave back and forth across the lane without leaving the protected zone. This width varies dramatically between different resonances. Strong resonances like the 2 to 3 relationship have very wide protective zones. Weaker resonances offer narrower safety margins but still provide meaningful orbital stability. The boundaries aren't fixed. Resonance width changes over time as the giant planets slowly evolve their own orbits. Some zones gradually expand while others contract. Objects can find themselves moving between different resonant neighborhoods over geological timescales. This flexibility explains why resonant capture was so successful during planetary migration. Objects didn't need to hit precise orbital targets to find stability. The wide resonance zones provided generous landing areas for ILDs fleeing the gravitational chaos of the early outer solar system. The transition between stable and chaotic regions in the Kuiper Belt isn't gradual. It's shockingly abrupt. Cross an invisible line in orbital space, and predictable motion instantly becomes chaotic randomness. These chaos boundaries exist wherever different resonances overlap or interfere with each other. Like standing waves in a pond, the gravitational influences create regions of constructive and destructive interference. An ice world can orbit peacefully for millions of years just inside a stable zone. Then a small gravitational nudge pushes it across the chaos boundary. Within a few thousand years, its orbit becomes completely unpredictable. Computer simulations reveal these boundaries as knife-sharp lines in orbital space. Move just slightly in the wrong direction, and orbital stability vanishes instantly. The mathematical precision of these boundaries defies human intuition about gradual transitions. The chaos boundaries act like gravitational trash disposals. Objects that wander into chaotic zones typically get ejected from the solar system within a few million years. These invisible boundaries have been clearing out unstable orbits for billions of years, leaving behind only the objects fortunate enough to avoid crossing the chaos lines. Astronomers have created detailed maps of orbital stability throughout the Kuiper Belt region. These gravitational charts reveal a complex landscape of safe neighborhoods and dangerous districts. The stability maps look like aerial views of a city. Stable zones appear as green islands of safety. Chaotic regions show up as red zones of danger. The boundaries between them create intricate patterns that change with orbital distance and inclination. Each point on the map represents a potential orbit. Green areas promise billions of years of stable motion. Red areas guarantee rapid orbital decay. Yellow zones offer temporary stability that eventually gives way to chaos. The maps reveal hidden structure in what appears to be empty space. Certain orbital combinations provide exceptional long-term stability. Others lead inevitably to gravitational disaster. These cosmic zoning charts help astronomers predict the future evolution of ice world populations. Objects currently in green zones will likely survive for the solar system's remaining lifetime. Those in red zones face imminent ejection. The maps provide a glimpse into the gravitational future of the outer solar system. The most sophisticated resonances involve multiple objects simultaneously. These 3-body or 4-body resonances create gravitational partnerships more complex than any 2-object relationship. In a 3-body resonance, the orbital periods of 3 different objects lock into a mathematical relationship. Object A might complete 5 orbits, while Object B does 3 and Object C finishes 2. All 3 maintain this precise timing for millions of years. These multi-body relationships require extraordinary fine-tuning. All participating objects must maintain exact orbital synchronization. If any partner falls out of step, the entire resonance system can collapse. The complexity increases exponentially with each additional participant. 4-body resonances involve even more intricate mathematical relationships. Some theoretical resonances could involve 5 or more objects dancing in perfect gravitational harmony. These multi-body resonances represent the most sophisticated examples of gravitational organization in the solar system. They demonstrate that mathematical relationships can coordinate the motion of entire groups of worlds across vast distances and timescales. The Kuiper Belt contains examples of cosmic choreography that rivals the complexity of any human-designed system. Around young stars across the galaxy, astronomers observe something remarkable. Vast disks of gas and dust swirl in perfect spirals. These aren't just pretty cosmic decorations. They're planetary construction sites actively building new worlds. These protoplanetary disks contain all the raw materials needed for planet formation. Gas provides the bulk. Dust grains serve as building blocks. Ice and rock mix together in the outer regions. The entire disk rotates like a cosmic pottery wheel, slowly assembling the components for future solar systems. The disks stretch for billions of miles around their central stars. Most of the action happens in specific zones at different distances. Rocky planets form closer to the star where temperatures are high. Gas giants assemble in the middle regions. Ice worlds like our Kuiper Belt objects grow in the cold outer reaches. These construction projects take millions of years to complete. Astronomers can observe planetary systems at every stage of development. Some disks show smooth, undisturbed material still waiting to be organized. Others reveal gaps and rings carved by newly formed planets. Protoplanetary disks prove that our solar system's formation wasn't unique. The same construction process happens around stars throughout the galaxy. Every planetary system started as one of these rotating cosmic workshops, where gravity slowly transforms dust into worlds. What happens after planets finish forming? The leftover construction materials don't just disappear. They create something astronomers call debris disks, cosmic junkyards filled with the remnants of planetary formation. These debris disks are like archaeological sites. They preserve evidence of completed planetary construction projects. The remaining dust and small objects tell stories about what kinds of planets formed and how the construction process unfolded. Unlike the gas-rich protoplanetary disks, debris disks contain mostly solid materials. Dust particles from grinding collisions, rocky fragments from failed planet formation, ice chunks that never got incorporated into larger worlds. The debris creates a detectable infrared signature. When starlight hits the dust particles, they warm up and glow in infrared light. Space telescopes can detect this excess infrared emission from light years away. This observational technique has revolutionized our understanding of planetary system architecture. Debris disks reveal the presence of Kuiper Belt-like regions around other stars. They show that our solar system structure, with an inner zone of rocky planets and outer regions of ice and debris, represents a common cosmic pattern. Vega was supposed to be a normal star, bright, hot, and relatively young. Then the infrared astronomical satellite detected something unexpected. Vega was glowing too brightly in infrared light. The excess infrared emission meant something was absorbing Vega's starlight and re-emitting it as heat. That something turned out to be a vast disk of dust surrounding the star. This discovery marked the first detection of a debris disk around another star. The Vega disk extends much farther than our solar system. It starts at about 30 times Earth's distance from the Sun and stretches to over 500 times that distance. For comparison, our Kuiper Belt sits at just 30 to 50 times Earth's distance from the Sun. Computer models suggest the dust comes from collisions between larger objects. Rocky asteroids and icy comets grind against each other, creating clouds of fine particles. This grinding process has continued for millions of years. Vega's debris disk proved that our solar system isn't alone in maintaining populations of small rocky and icy objects. The infrared signature revealed an alien Kuiper Belt, the first evidence that other stars harbor cosmic junkyards similar to our own. Fomalhaut hosts one of the most photogenic debris disks in the galaxy. Unlike the smooth, fuzzy disk around Vega, Fomalhaut's debris forms a sharp, well-defined ring. The precision is almost too perfect to be natural. The ring sits about 140 times Earth's distance from Fomalhaut. It's remarkably narrow, only about 15 times Earth distance wide. The inner and outer edges are so sharp they look like they were carved with cosmic precision tools. Such sharp boundaries don't occur naturally. Random collisional processes create fuzzy, gradual edges. The knife-sharp structure of Fomalhaut's ring demands a different explanation: gravitational shepherding by unseen planets. Astronomers suspect that massive planets orbit just inside and outside the debris ring. These shepherd planets act like cosmic snowplows, clearing out debris from certain regions while confining it to narrow zones. The shepherding mechanism works exactly like Saturn's rings. Moons orbiting just inside and outside specific ring zones create gravitational resonances that maintain sharp boundaries. Fomalhaut's debris ring operates on a vastly larger scale but follows identical physical principles. HR 4796a presents astronomers with a cosmic mirror. This star system's debris disk shows striking similarities to our own Kuiper Belt. The resemblance suggests common architectural principles govern planetary system formation. The debris ring around HR 4796a sits at just the right distance to represent an alien Kuiper Belt. It extends from about 45 to 75 times the Earth-Sun distance, remarkably similar to our own Kuiper Belt's boundaries. The disk shows the same basic structure as our solar system. An inner region cleared of debris suggests terrestrial planets formed close to the star. The outer debris ring indicates ice world formation in the cold outer reaches. Even the disk's mass matches theoretical predictions for a Kuiper Belt analog. The total amount of material falls within the expected range for planetary formation leftovers. The size distribution of particles also matches computer models of collisional evolution. This remarkable similarity suggests that solar systems, like ours, aren't rare cosmic accidents. The same physical processes that shaped our planetary neighborhood operate around other stars. HR 4796a represents what our solar system might look like to alien astronomers studying it from afar. Debris disks aren't static structures. They evolve constantly through an ongoing cosmic demolition derby. Objects constantly collide, shatter, and get ground down into smaller and smaller pieces. The collisional cascade starts with the largest objects. Planet-sized bodies crash into each other, creating clouds of smaller fragments. These fragments collide with other fragments, creating even smaller pieces. The grinding process continues relentlessly. Asteroid-sized chunks break into pebbles. Pebbles get pulverized into dust grains. Dust particles collide and sometimes stick together, but they can also get shattered into even finer material. Computer simulations show this process taking hundreds of millions of years. The debris disk gradually becomes dominated by smaller and smaller particles. Eventually, radiation pressure from the central star blows away the finest dust, leaving behind only the larger fragments. This collisional evolution explains why older debris disks appear fainter than younger ones. The grinding process gradually reduces the total amount of detectable material. What starts as a bright, dust-rich disk slowly fades into a sparse collection of larger objects that produce less infrared emission. Hidden planets act as cosmic architects in alien debris disks. These unseen worlds use their gravitational influence to carve complex patterns in the surrounding debris. The result is organized structure where chaos should reign. Shepherd planets operate like gravitational snowplows. They clear out debris from certain orbital zones while concentrating it in others. A massive planet can create a completely debris-free gap in an otherwise uniform disk. The shepherding effect extends far beyond the planet's immediate neighborhood. Gravitational resonances allow planets to control debris motion at distances many times their own orbital radius. A single massive planet can organize an entire debris disk. Some alien systems show multiple rings and gaps, evidence of several shepherd planets working together. Each planet carves its own zone of influence. The combined effect creates intricate patterns that reveal the hidden planetary architecture. This gravitational sculpting provides astronomers with a powerful tool for detecting alien planets. Even if the planets themselves remain invisible, their gravitational fingerprints show up clearly in the debris disk structure. The organized patterns serve as cosmic signposts pointing to hidden worlds. Debris disks aren't eternal. They fade away as their host stars age. This cosmic aging process reveals how planetary systems evolve over billions of years. Young stars typically host bright, massive debris disks. The infrared emission can be hundreds of times stronger than what we'd expect from dust alone. These systems are still experiencing active planet formation and massive collisional activity. Middle-aged stars like our Sun show much fainter debris signatures. The most violent phase of planet formation has ended. Only gentle grinding between smaller objects continues. The infrared excess becomes much more subtle. Ancient stars often show no detectable debris at all. Either the original material got completely ground down and blown away, or it got incorporated into planets and removed from the disk entirely. This age progression suggests that our solar system's Kuiper Belt represents a mature debris disk. We're observing the calm aftermath of violent early planet formation. The current population of ice worlds is just a small remnant of the original construction materials. No two debris disks look exactly alike. Each star system creates its own unique pattern of leftover material. This diversity reveals how local conditions shape planetary system architecture. Some systems create multiple rings at different distances. Others produce single broad disks. A few show highly asymmetric patterns with clumps and gaps in unexpected places. The variety depends on many factors. The star's mass and brightness affect how planets form and migrate. The original amount of material determines how much debris survives. The presence and configuration of giant planets shape the final structure. Even the stellar environment matters. Stars in crowded regions face different evolutionary pressures than isolated stars. Binary star systems create entirely different conditions than single stars like our Sun. This diversity suggests that our solar system represents just one possible outcome from planetary formation. Other configurations might be more common. Our particular arrangement of planets and debris might actually be relatively rare in the galaxy. Current telescopes can detect alien debris disks, but can't resolve individual objects within them. That's about to change. The next generation of space telescopes promises to revolutionize our understanding of alien Kuiper belts. The James Webb Space Telescope already provides unprecedented infrared sensitivity for detecting faint debris signatures. Future telescopes will push even further. They'll have the resolution and sensitivity needed to image individual large objects in nearby debris disks. Advanced coronagraphs will block out starlight to reveal much fainter objects orbiting close to the star. Interferometric techniques will combine light from multiple telescopes to achieve resolution equivalent to instruments hundreds of miles across. These technological advances will allow astronomers to conduct detailed surveys of alien ice worlds. They'll measure sizes, compositions, and orbital properties of individual objects. They'll track how these populations evolve over time. Within the next few decades, we may have complete inventories of ice world populations around nearby stars. We'll finally be able to compare our Kuiper Belt in detail with its alien counterparts. This comparative planetology will reveal which aspects of our solar system are universal and which are unique products of our particular cosmic neighborhood. New Horizons changed everything we thought we knew about the Kuiper Belt. Before this spacecraft, ice worlds seemed like dead, frozen rocks drifting in eternal darkness. The mission's discoveries shattered every assumption. The spacecraft visited Pluto in 2015. The images it sent back stunned scientists worldwide. Pluto wasn't dead at all. It was vibrantly active. Nitrogen plains stretched across the surface. Mountain ranges made of water ice towered miles high. Complex weather systems moved across the landscape. The New Horizons continued deeper into the Kuiper Belt. It encountered an object called Arakoth, a primitive contact binary that looked like a cosmic snowman. This encounter revealed how the original building blocks of planets stuck together billions of years ago. These close-up visits provided the first detailed portraits of Kuiper Belt residents. They proved that these distant worlds are complex, dynamic places with their own unique personalities and geological histories. New Horizons transformed ice worlds from mysterious dots of light into real places with landscapes, weather, and fascinating chemistry. The mission opened our eyes to the incredible diversity and activity hidden in the solar system's frozen frontier. Future missions won't stop at just one Kuiper Belt object. Engineers are designing spacecraft that can visit multiple ice worlds during extended grand tours of the outer solar system. These multi-target missions face enormous technical challenges. The distances between objects are vast. The flight times stretch across decades. Spacecraft must remain operational far longer than any previous deep space mission. The key breakthrough involves advanced propulsion systems. Ion drives and nuclear-powered engines can provide the sustained thrust needed for complex trajectories. These technologies allow spacecraft to change course multiple times during their journeys. Mission planners are developing elaborate orbital choreography. Spacecraft will use gravitational assists from giant planets to reach multiple targets. Each flyby will be precisely timed to maximize scientific return while conserving fuel. The multi-object approach will revolutionize our understanding of ice world diversity. Instead of studying individual objects in isolation, we'll compare entire families of Kuiper Belt residents. These comparative studies will reveal how different formation conditions created the variety we observe today. Current missions zoom past their targets at high speed. Future orbital missions will slow down and stay for extended observations. This represents a fundamental shift from quick snapshots to comprehensive surveillance. Orbital missions require dramatically more energy than flyby encounters. Spacecraft must carry enough fuel to break into orbit around their targets. This makes them much heavier and more expensive than simple flyby probes. The scientific payoff justifies the extra cost and complexity. Orbital observations can map entire surfaces in detail. They can monitor seasonal changes as ice worlds travel around their elongated orbits. Long-term orbital studies will reveal dynamic processes invisible to brief flyby encounters. Seasonal atmospheric changes, surface material migration, possible geological activity. These phenomena unfold over months or years, too slowly for flyby missions to detect. The first orbital missions will target the largest and most accessible dwarf planets. Success with these initial targets will pave the way for more ambitious orbital surveys of smaller, more distant ice worlds throughout the Kuiper Belt. Sample return missions represent the holy grail of Kuiper Belt exploration. Bringing actual pieces of ice worlds back to Earth would revolutionize our understanding of solar system formation and the potential for life. The technical challenges are staggering. Spacecraft must travel billions of miles to reach their targets. Collect samples from the surface, then return those samples to Earth while preserving their chemical integrity. The journey time alone poses enormous difficulties. Round-trip missions to the Kuiper Belt take several decades. Spacecraft systems must remain functional throughout these extended odysseys. Sample preservation creates additional complexity. Ice world materials contain volatile compounds that evaporate at relatively low temperatures. Keeping samples frozen during the long journey home requires sophisticated cryogenic storage systems. Despite these challenges, sample return missions would provide unprecedented scientific value. Earth-based laboratories can perform analyses impossible with remote spacecraft instruments. They can detect trace compounds, measure isotope ratios, and search for complex organic molecules that might provide clues about the origins of life itself. Surface exploration missions will put robotic landers directly onto ice world terrain. These mechanical explorers will drill into frozen surfaces to extract samples from below ground. Landing on ice worlds presents unique engineering challenges. The extremely low gravity makes traditional parachute landings impossible. Spacecraft must use rocket thrusters for precise powered descents onto unknown terrain. Surface operations face harsh environmental conditions. Temperatures near absolute zero make most materials brittle. Electronic systems must be specially hardened to function in extreme cold. Solar panels provide minimal power at such distances from the sun. Drilling through ice world surfaces requires specialized equipment. Conventional drill bits would shatter in the extreme cold. Engineers are developing heated probes that can melt through frozen materials while collecting samples. These surface missions will answer fundamental questions about ice world composition and structure. Subsurface drilling can reveal layered histories preserved in the frozen ground. Each layer represents a different epoch in the object's evolution, creating detailed geological records spanning billions of years. Ground-based telescopes are getting dramatically more powerful. The next generation will discover ice worlds faster than we can name them. These astronomical surveys will map the entire Kuiper Belt population in unprecedented detail. The James Webb Space Telescope has already begun detecting smaller and more distant objects than ever before. Future telescopes will push these limits even further. They'll spot ice worlds the size of large asteroids throughout the outer solar system. Advanced computer algorithms will automate the discovery process. Artificial intelligence systems will scan millions of telescope images, looking for the telltale motion of distant objects. Human astronomers won't be able to keep up with the discovery rate. These surveys will reveal the true extent of ice world populations. Current estimates suggest tens of thousands of large objects exist in the Kuiper Belt. Future telescopes will provide complete census data for objects down to much smaller sizes. The discovery explosion will transform our understanding of outer solar system architecture. Complete population surveys will reveal subtle orbital patterns invisible with small sample sizes. They'll provide the statistical foundation for testing theories about planetary migration and solar system formation. Future Kuiper Belt missions will carry artificial intelligence systems capable of making autonomous scientific decisions. These smart spacecraft won't need constant guidance from Earth-based mission controllers. Communication delays make real-time control impossible at Kuiper Belt distances. Radio signals take hours to travel between Earth and the outer solar system. By the time mission controllers receive data and send commands, opportunities for observation might be lost. AI systems will analyze incoming data in real time and adjust mission plans accordingly. If sensors detect unexpected surface features, the AI can automatically redirect instruments for detailed study. If atmospheric conditions change, it can modify observation sequences to capture the new phenomena. Machine learning algorithms will improve throughout the mission. As AI systems gain experience with ice world environments, they'll become better at recognizing scientifically interesting features and phenomena. These autonomous capabilities will dramatically increase mission efficiency. Instead of following predetermined observation schedules, smart spacecraft will continuously adapt their activities to maximize scientific return. They'll essentially become robotic field geologists capable of making discovery-driven decisions millions of miles from human oversight. No single country can afford the most ambitious Kuiper Belt exploration programs. Future missions will require unprecedented international collaboration to share costs and technical expertise. The expense of deep space missions grows exponentially with distance and complexity. Sample return missions to the Kuiper Belt could cost tens of billions of dollars. Even the wealthiest space agencies can't justify such expenditures for purely national programs. International partnerships offer solutions to these financial challenges. Multiple countries can contribute different mission components. One nation might provide the spacecraft bus. Another supplies scientific instruments. A third handles launch services and mission operations. These collaborations also combine complementary technical strengths. Different space agencies have developed expertise in different areas. Japanese agencies excel at sample return systems. European teams have mastered long-duration spacecraft operations. American organizations lead in nuclear power systems. The collaborative approach will create mission capabilities no single agency could achieve alone. Shared costs make ambitious projects financially viable. Combined expertise produces more sophisticated spacecraft. International cooperation transforms impossible dreams into achievable realities for exploring the solar system's frozen frontier. The Kuiper Belt contains vast quantities of water ice and other valuable materials. Future space exploration might transform these ice worlds into resource extraction sites for deep space missions. Water ice serves as the ultimate space resource. It can be split into hydrogen and oxygen for rocket fuel. It provides drinking water for human crews. It offers radiation shielding for spacecraft. A single large ice world contains enough water to fuel thousands of deep space missions. Robotic mining operations could extract and process ice world materials. Automated systems would mine frozen surfaces and convert raw materials into useful products. Solar-powered refineries would operate continuously in the perpetual darkness. The extracted resources would support expanded human presence throughout the solar system. Mars missions could refuel at Kuiper Belt depots during their journeys. Interstellar probes could top off their tanks before leaving the solar system entirely. This resource utilization would transform the Kuiper Belt from a scientific curiosity into a strategic economic asset. Ice worlds would become stepping stones for human expansion into deep space. The frozen frontier would evolve from exploration destination into industrial infrastructure supporting humanity's cosmic ambitions. Kuiper Belt exploration represents far more than studying distant ice worlds. These missions will fundamentally transform our understanding of how planetary systems form and where life might emerge throughout the universe. Ice worlds preserve the original materials from which all planets formed. Studying their composition reveals the chemical ingredients available during the early solar system. This information constrains models of planetary formation throughout the galaxy. The organic chemistry found on ice world surfaces might provide clues about life's origins. Complex carbon compounds form naturally through radiation processing of simple ices. These materials represent the building blocks from which life eventually emerged on Earth. Comparative studies of different ice world populations will reveal how planetary formation varies under different conditions. This knowledge applies directly to understanding exoplanet systems discovered around other stars. Future Kuiper Belt missions will answer some of the most profound questions in science. How do planetary systems form? What role does chemistry play in creating habitable worlds? Could life emerge in environments very different from Earth? The frozen worlds at our solar system's edge hold keys to understanding our cosmic origins and our place in the universe.